Hello, welcome and good evening to the third part of our Let's Code episode on the Node MCU or ESP8266. And last time we started off by using the CO2 and TVOC sensor, and today we want to enhance this a bit because the TVOC and CO2 sensor use a heating element which is susceptible to environmental temperature changes and also humidity. It is common that you get these boards with a temperature and humidity sensor on board, or you can attach your own sensor. And the good thing about that is that you also get like measurements for room temperature and humidity. And one of those modules is this one here. This is a BME280 280, and I think this is made by Siemens or Bosch. And it's this teeny tiny little square sensor here with a little hole inside, and there's only 2 capacitors and 4 little resistors here on that side and nothing else. And it's again an I2C device. We only have to put in 3.3 volts VCC, ground, and then SCL and SDA for the I2C, and the rest we actually don't need. So yeah, we will enhance our program and to use this thing as well. So I changed the wiring here a bit because we will also use a slightly different library this time. I figured out since the last time that Sparkfun actually has open source libraries for both devices, and they play well together, pretty well together, obviously, because they also make parts that with both of them on board, or you can buy each separately, and everything from Sparkfun is open source anyway. So yeah, it's a very nice solution, and the library is very similar. The CCS811 library is basically almost identically to be used as the old library, so there's little change. And this library is also pretty straightforward. And this time I will also do a more let's code-ish approach where we actually will write the program from scratch. Yeah, so the wiring up is very similar, as I said. I will put this back on the breadboard and explain the wiring very quickly. So the most important outputs here are D6 and D7, and actually D8 is, I think, also used for ground, but you can also just attach it to the ground plane anyway. Okay, D6 and D7 are SDA and SCL respectively, and we will wire this up first here to the BME chip and then bridge it over to the CCS chip. And what you can't see here, I will remove this, is that I've put 3 volts and ground on these 2 rails, on the ground and the positive rail, bridged it over here to these 2 rows, and then pass it over to the other chip as well. So the top 2 rows over the whole breadboard are basically VCC and ground. So I can just attach both very symmetrically here because they both start off with VCC and then ground, then SCL and then SDA. So we really get a nice little bus here. And only the wake up pin needs to be wired to D8 or to ground. Doesn't matter what you choose, as long as this wake up pin is pulled to ground, the chip will work. Alright, and that's already the whole wiring up. So we can attach the device and start coding, I would say. Okay, first thing that you need is to download both the CCS811 library from Sparkfun and the BME280 library from Sparkfun as well. And you can do this as usual by just going to the GitHub page, which I'll link to in the video description, and click download a zip for both libraries, and then you can import them into the Arduino IDE. Also, if you want to see what kind of functions both the libraries offer, You can browse the source, and it also comes with a bunch of documentation. Here's the Sparkfun CCS sensor. It looks a little bit different from ours, but they are all, of course, compatible. And Sparkfun does some very nice stuff. Everything's open source, the hardware designs, the libraries. So go and support them. Although I have to admit, their breakout boards are, of course, a bunch more expensive than the cheap Chinese knockoffs that I'm currently using. But nevertheless, check out the site and maybe you'll find some good stuff at their place. Okay, anyway, their BME board actually also contains the CCS, so you even get like this double package and you only need one board. I took both separately, which is also nice sometimes if you only want one of the sensors. And this, of course, will make it also a bit more expensive, probably. But yeah, so if you want to look at the source, just browse to the source directory and go to the header file, and then you can see what the API looks like. There's a bunch of defines, and then there's the CCS811 core class, but you will be using the CCS811 class, and it will have a begin function, and you can read the results of the measurements but before you have to check if data is available. And of course you can also check for errors and stuff like that. And after reading the results of the measurement, you have to actually call the get tvok and get CO2 functions because the algorithm result will just say if there was an error or if it was a success, and then it will store all the stuff in the private members. So it's a pretty simple API. And for the BME sensor, it looks similar. If we look at that, there will be as well a bunch of defines, first of all, and some sensor settings, and then the BME280 class, which is the most important one, also with a begin function, which will also return some kind of status. And you can either interface via SPI or I2C. We'll of course use I2C because that's how we also wired up the CCS chip. And then you can read the pressure and the temperature in Celsius or Fahrenheit from the device. And that you can actually use back in the CCS to feed into the environmental data to calibrate the results better. So set environmental data takes a relative humidity and a temperature in Celsius, which should in theory lead to better and more accurate results. Okay, so let's start using those two libraries. We start off with a fresh and empty sketch, and after importing the libraries, which you can do in your Arduino IDE, just like this, adding a zip library, sorry for the German here. You can actually add everything. First of all, we need the wire library, which allows us to use I2C. And we will also use the Sparkfun BME library and the Sparkfun CCS library. And I actually don't like the way this thing includes everything because wire is part of the core Arduino. I will put it here. So the very first thing that we'll do is do the setup. And to be on the safe side, we will wire first of all the wake up pin of the CCS chip to be on ground and on a special pin, namely D8. So we'll define a couple of constants here for easier usage. So the CCS811 wake up pin will be D8. Also we will define the pins for SDA and S clock of I2C. So pin CCS811 SDA will be D6, and let's copy that for SCL, this is the I2C clock, will be D7. Before I said that you can actually put this just to ground, but in the examples they show that you should disable the CCS chip while doing the readout of the BME. And we will do that here as well. So I picked this straight from the examples. Alright, so first let's set up the pins. For this, Arduino has the pin mode, and you just pass it the pin. And in this case it's a CCS811 wake up, and we say, yeah, we want to do output on this, not reading. And first of all, we will write to the same pin here a 1 to enable the chip, and later we'll disable it and re-enable it after reading of the BME. Also, we will enable serial monitoring. So we will say serial begin and then the baud rate, and we set it here to 115200. And we'll print some greeting. And here we'll introduce a utility function called print. That's a very useful function that I found in the examples to the library. And yeah, it allows you to do printf style formatting on the serial port, which is not available by default. So we'll write out a little greeting, CO2, T-Walk, temperature, humidity, sensor. And yeah, let's define this print function. So usually you have printf, right? And with printf you can write something like printf foo %u and then some integer variable. And this will correctly format so that %u will be replaced with integer value. More complex examples would be floating point variable with, let's say, 2 decimal places. Then you could say float val, and of course you can put multiple parameters in here. The same we want to do here, so we define a function called print, and just like the printf function, it will take a string, which gives the format, and then a variable number of arguments. And in C, you write the variable arguments like 3 dots. And there are macros to actually expand this to a useful parameter list. So the output that we actually want to produce will go into a buffer, and we have to limit it. We will limit it to 256 bytes, which should be fine. If it's not enough, you can enlarge this. And then we use the macro VA list to, no, I think this is actually a type. This is not yet a macro, but there's a type variable argument list, and it will take the arguments that follow here for the 3 dots. And then the macro VA start will expand these things into the argument list. And yeah, format is the first argument. And we will end this by using VA and arguments. Okay, in between we'll call a special printf variant. So usually you would just say printf format arguments, and this will call the printf function just as is. But there's a function which takes variable argument lists, that's the vprintf variant, and that actually prints to a string buffer up to n bytes. So we're actually looking for the vsn printf function. Very useful. You can actually look all this up in the C programming manuals. Also, usually a good idea is a site called devdocs.io, and it has also documentation on C. And you can simply search C and say vs and printf. Here we are already. And it will tell you what it takes. It takes a strict buffer, a strict format, and a variable argument list. And the VSN, we're actually looking for this. And a buff size here. Restrict buffer buff size, restrict format, and a variable argument list. So you can look all this up whenever you want to. So what we need to add here is the target buffer. It will be buff, and the length of the buffer you can query with size of. This actually only works for these compile time defined things. So here you can actually use size of. If you have a pointer, this will not work. There you would need to use something. You would basically have to know how much memory was allocated. But here for the statically allocated stuff, you can do size of. Okay, so in the end we will have the resultant buff, and we just need to write it out on the serial port. And for this we have the write function, and we just pass it the buffer. Let's check if this works. And yeah, that looks good. CO2, T-Bog temperature, humidity sensor. Perfect. After we have this, we need to set up a little bit more, right? So we need to enable I2C. And this is done by calling wire begin. And we pass it the SDA and the SCL pin. So basically we just copy these two lines, SDA and SCL, and that's already done for the setup of I2C. After that we can use I2C devices. Next up is initializing the BME280 library. So for the BME280 we have to start off with setting the I2C address, because actually the device can be on two different ports, either OX76, so hex 76, or hex 77. My device is actually running on address 76, but you can check for your own just by trial and error. So let's put OX76 here. Then we do check if this actually works. So the BM280 has, when we take a look here, a begin I2C, or a begin I2C function, and it will return a bool with true or false depending on if it was successful or not. So we call begin I2C with no parameters because we're using the wire library. And if that equals false, then we have a problem. So we write something like fail to initialize BME280. And there's a little trick I learned. When you put an infinite loop here, the device will actually reboot until it actually works, or it will be stuck in a reboot loop, but then you have different problems. But you can do that. Let's put an else path here as well, so we see if it was successful. Found BME280 or something. And we could test this already, but I'm feeling lucky, and we will just go on and also initialize the CCS811. And for that, we will write, actually I think I was wrong. As I said in my last episode, writing out a 1 will actually pull the pin low for some reason. And will it? No, it will pull high. Because for enabling we actually have to pull it low. So this was correct. So this disables the chip. It won't do anything. It won't interfere with the BME or something. It will pull low and disable, pull high and disable the chip. And now we will do the same, but with a 0. So now we will pull the pin low, and this will actually wake up the IC. And then we can try to initialize the chip, and that works. How does this work? We have to take a look at the CCS811 core, and it has this begin core. No, we don't want that. We actually want, which function do we want? Actually, we take this one here, right? Yes, we want this one here. This one returns, what was it, begin? Exactly, we also take the begin, and it returns a status. Status is a member of CCS811 core. So we have CCS11 core status, and what do we call it? Return code or something. And we just call it on our object. Call the begin function, and then we can check if we were successful or not. So if the status is anything else than, let's see, CCS811 core sensor success, right? This is the only success that we are interested in. Then we have a problem. So we can more or less copy this whole shebang here. I will just write CCS811 and here as well. And that should actually do it. We will try that. Nope. What's our problem here? A bunch of problems. BME280 was not declared. Yeah, of course. We still have to declare something here, right? We don't have any variables. So let's make some static variables. CCS811. And it takes an address. And the address for this device is always 5A hexadecimal. So we keep that here. And that's actually necessary if you take a look at the constructor. It doesn't say here, but it's not documented very well. But this is the I2C port or address. And we'll also do an object for the BME, and it just doesn't take anything. So that should be fine. Okay, one more thing. Status was not declared. Yeah, of course, because it's not status, it's return code. And this is why live coding is a bad idea. Or maybe a good idea, I don't know. Yeah, as you can see here, found both ICs. That's very good news. We can now continue to actually code our run loop. First of all, we will check the CCS811 if there is new data available. Because if not, it doesn't make sense to actually do something. So if data is available, we can call the CCS811 read algorithm results function. And then we can actually read out the values for TVOC and CO2. So we'll store that here in TVOC. CCS811 get TVOC and also UN60T CO2. Same thing. And then we need to it would be best if we average these values, right? So we will make something to average that. And I'm also taking this straight from the example. So they introduce some structure called, let me check my notes. We define a structure called averager type. Oh, look at this, I'm typing too much. And this will have a large integer for the total and for the total amount that we summed up, and a 16-bit integer for the count. Alright, so we can use these averages, which we'll actually have to define somewhere. So at the top of the loop function, we'll put in two static variables of type averager t, and one will be the TVOC averager, initialized with zeros, and the other will be for the CO2. All right. So the TVOC averager, we will sum up the sum up the total amount. Same goes for the CO2 averager. Total. CO2 averager will also get the total amount incremented. And of course we need to increment the count, because then in the end we can average by dividing the total amount by the count. And we'll do that in a second. It's of course garbage, CO2 averager, count plus plus. Alright, that's fine. So now we collected all the data. And let's say we want to average over a 10-second period, because I think more real time doesn't make sense, and that's also what they suggested in the example. So we'll do just that. So if the time that has elapsed, which will be the number of seconds that are on our real-time clock now, minus the number of seconds that we spent until we, last time, for example, we logged something, we will compare that to the number of seconds that we usually log after. So we need to define some period for the logging, and we can do that up here. Let's do that real quick. Define log period seconds, and that will be 10. So after 10 seconds we want to log again. The question is, what are second and second log? So the Arduino gives us an unsigned long value by calling the millis function, which will give us the milliseconds since startup, and just divide this by 1000 so we get the number of seconds since startup. That's good enough for us. And we need to store the second log, of course. So we'll do another static variable up here of type unsigned long, name second long, and initialize it with 0. So now if this condition holds, we can store the current number of seconds in second log, because we know, okay, now we did the actual logging, and in the end we'll print something, right? So we can print something if we had at least one sample. So we take a look at the TVOC averager, for example, and if its count is greater than 0, we had at least one sample, and we can calculate the average. I will make it a 16-bit sample by casting the total to a float value, because otherwise we will get very inaccurate computations dividing two integer numbers. So we cast the total number by to a float and divide by, and this second cast is not strictly necessary, by the count. So the float casts are necessary, or at least one of them is necessary, because let's say you have some largish value, smallish value here and a large value here, you will get a 0. Actually, I'm talking crap, right? This is absolutely not necessary. So the problem will be, no, it's actually not should not be necessary. Let's take this out. Let's try it without this. I thought we needed, but maybe I'm talking out of my arse here. So let's see. Anyway, after we did the averaging, we can reset the averager. So we say total is 0 again, and also the count is 0. And of course, Same goes for the CO2, but first let's print out the value that we got. So we say tvoc %u, and we should put some new line in here, and we'll return that. And as I said, same goes for the CO2. So replace all the tvoc. I think we should be able to do that with search and replace. Does it have something like that? Yes, it does. So tvoc by CO2, replace, 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 replace. And I want to have this capital. So let's try this out. And we've got a bunch of problems here. Average T does not name a type. That is because we have done something wrong. It should be average a type. And then I think we should be fine. Almost. This should be total. And that should be all the errors, right? Yeah, these are all the errors. Yeah, we do get something. That looks good. CO2 value is around 400, so outdoors should have at least 400, and inside this room it's probably higher. Let's see if it changes over the next few seconds. Yeah, it changes a bit. Let's breathe on the device. And now the values should get much higher. Yeah, we get 1000 and also some volatile components. That's my breath. So this looks great. Wonderful. The only thing that's now missing is to read out the BME values. And that's actually also not that hard. So after doing this, we can do this a very, very, very similar thing, right? We can check every 10 seconds, let's say. And this time we don't call it log period, but it's the environmental data period, which we can also tweak via this constant here. And every 10 seconds we will have a second env, which should also be here. And we will reset that, and we will also store that. So let's put that up here. And this will keep track of the environmental data, temperature and humidity. And we will have to read out the temperature and the humidity. And for that, as I said, the examples say we should disable the 811 chip. So we will say the wake up will be set to 1. Remember, high is disabled. And after we're done, we'll write a 0 to pull it low to enable the chip again. So we'll read the temperature in Celsius, and let's check that again. That is somewhere down here, read temperature in Celsius. So that goes here, and we should pass that to the object actually. And we'll have humidity, and that is float pressure? No. Oh, it can do pressure, that's interesting. Humidity, we want humidity. But pressure is also nice, didn't know that it could do that. That's good, yeah, we have that now. We can print that, because that's useful information as well. We want to see what we get here. So temperature is some float value, so we'll put with two significant digits, and humidity as well, %.2f, percent, and maybe a new line should be good, and this will be temp C and humidity. And the last thing to do is to set the environmental data. First takes the relative humidity and then the temperature. So temp C and humidity. And that's all we need. So the chip is enabled again, we write the data, and that's good. And this should in theory help you make better measurements. Let's compile and test. And there's something wrong, of course. Humidity. Oh no, set environmental data was not declared. Of course, because it's part of the CCS811 object. Try again. Right, here we are. Let's see if it works. Hopefully. 10 seconds have to pass, and yeah, here we get 25.95 degrees. It feels less warm, and a pretty dry 29% relative humidity. Not sure about the accuracy of this stuff, but it's at least roughly correct. I should get a real thermometer and test this. But you see, it at least works. You have to run this chip for 48 hours is what so at least I think the CCS, that's what the manufacturer says, to get decent values anyway. And there's also the possibility to store the baseline values in the non-volatile memory of the ESP to get even faster calibrated results. It's on the examples, you can check them out, but now we already have quite good understanding, I think, of the workings of the BME and the CCS ICs for collecting this data. And in the next episode we will build a nice web front end so that you can pull this data graphically with a nice chart from your mobile phone or whatever without the need of extra servers and stuff. But this is basically the backend, and that's already pretty nice, I would say. And we already have a very long video now, so I hope you learned something here. I hope you enjoyed it. If so, please do give it a thumbs up. Also share it on your social media, and most important of all, if you haven't subscribed, please do. We are now above 230 subscribers, still a way off from the 1000, but I'm sure we can make it. So thanks for watching and have a nice evening.